Good morning, everyone. I welcome everyone for the day 7, 401st session, lecture 18, Ammonia role in carbon neutral industries. So, what is the objective? So, what is the objective of, I can say, going through this particular topic is to understand the fundamentals of ammonia, the carbon-free compound. Also explore the ammonia's application in carbon neutral industry. To evaluate the future potential of ammonia in achieving carbon neutrality, to discuss the benefits and challenges of ammonia adoption. Wherever you can able to, I can say either by some percentage of replacement with conventional fuel or the sole replacement wherever possible in the industries, we can able to think about in bringing ammonia, that is green ammonia. So by replacing the conventional fuel like coal, other kind of fuels, I can say liquid or gaseous fuel, we can able to reduce the carbon dioxide emission comes out from the industry. So the end of the presentation, we can able to understand how to produce the green ammonia, what is carbon neutrality, why ammonia is important for carbon neutral industries, role of ammonia applications, challenges facing in green ammonia. In general, the major industries, what we are focusing on, conventional, I can say about the 80% of the power comes out from the conventional way of thermal power plant. The amount, the maximum power generated is used for the, I can say, different industries, particularly mining industry, food industry, leather industry, cement industry, petrochemical industry, agricultural industry. The major focus is how to, I can say, replace the usage of the conventional fuels. The first one is thermal power. Most of the thermal power plant in India is operated majorly with coal. Majorly with coal. Then steel industry. Cement industry. Other industry. Similarly, you have the food industry, several industries are there. So, whatever make the energy in the form of heat or the power in terms of electrical power, we are producing majorly from the thermal power. We can bring this ammonia. You all know that whether it is a thermal power plant or a gas turbine or generation system, we are using fuel, can say coal. We are using, I can say, air, the oxidizing medium, along with the ignition source. So there are three parameters going to be very important for combustion. So in general, the combustion, the fuel reacts with oxygen, produces fluid gas. That is the products of combustion, which has the heat. The fluid gas contains carbon dioxide, carbon monoxide, oxides of nitrogen, if the fuel contains sulfur, SOx, then unburned, I can say, hydrocarbons. Okay, this is with respect to thermal power plant I'm talking about. So in order to know how much the CO2 or CO is going to be generated, as I already mentioned that, go for ultimate and proximate analysis. Theoretically also you can able to find out how much the exact quantity of oxygen I need to provide so that I will get only CO2, water vapor, then cannot avoid the oxides of nitrogen. The fuel has natural coal has sulfur in nature, the salts. The combustion is perfect. So in general, we are providing a little excess here to avoid the formation of carbon, unburned hydrocarbon and the carbon monoxide. Okay. Now, so here, as the fuel contains hydrocarbon, carbon and nitrogen, the products of combustion we are going to get. The products of combustion you are going to get CO2. You are going to get CO2. So as I said, 80% of the power produced for various application comes through the thermal power plant. Then the CO2 emission not going to be avoidable. Correct? Now, how to bring down? How to bring down the CO2 emissions to 0% or CO2 emissions drops down. Assume that CO2 emission is around, I can say, 100 million tons per day. Forget about the capacity and all. So, in India, we are producing 100 million tons of CO2 comes out from the steam power plant. I want to bring it down to 0. It will take its own time. So, need to follow the road map. Or you can, I can say, I will bring down. I can say now in 2024, producers, we are producing 100 million tons per day. Maybe after 5 years or 2030, I want to bring down at least 50% drop in the CO2 level, approximately 50 million tons per day. Without I can say, within the existing system, right? So one of the option is go find it. Along with the coal of hydrocarbon, we are going to use ammonia. So people already start working on it. Normally, the ammonia generally we are using in steam power plant or in the engine side, right? To reduce the oxides of nitrogen. So I am going to modify the system, existing system, which are already running with coal, hydrocarbon, 100%. So I am going to produce flue gas. I can say which is CO2. Okay. So my objective is without modifying the existing system. So there are so much of amount was invested. So I don't want to, I can say, completely eliminate the usage of steam power plant. I can able to bring down from 100%, I can say 100 million tons per day to my objective is target is 50 million tons per day within I can say 6 years time from 2024. So you need to find out some kind of fuel which is not having carbon dioxide, carbon, or you can say you can use some fuel which is having the carbon value lesser than the what is the fuel we are currently using. Okay. So here we are not going to bother about the lower carbon or something. We can completely because we have the infrastructure to use ammonia. Already we have the facility to produce ammonia plenty. So you can provide ammonia here. So by assume that there are different cases where the target can be added because the calorific value of ammonia is comparatively, I can say 50% or
I can say 40% of calorific value of the coal, approximately I can say. Now, I am going to find out the energy content, how much energy content I need at the inlet, so that I can produce the required power output from the, I can say, steam power plant. Because you need ultimately, you are going to burn the fuel in the furnace. So fuel and air reacts in the presence of ignition source. You are producing the heat. That heat can be absorbed by the water which is circulated inside the tube, the boiler. So that is the working fluid. The steam which is coming out from the boiler is going to be the working fluid for producing the power in the steam turbine. Okay. Now I am going to use, instead of using a single fuel, I can use coal along with carbon-free fuel, ammonia. So here I can say, maybe I can say 100 tons per hour. I can say, coal is entering to produce, I can say, 100 million tons per day of CO2 or something. For example, I am saying. Now I can reduce it to 90 tons per hour coal by putting, maybe I can say 15 or 20% because it depends on the calorific value. Assume that now to meet the calorific value of the coal, I need 2 times the calorific value, 2 times the flow rate of, I can say, 2 times the ammonia flow rate. Right? Now I am going to use fuel is blended with coal, blended with ammonia. By doing so, I can be able to not only controlling the CO2 which is coming out from the I can say the boiler, or also I am going to control the oxides of nitrogen. Because to break the ammonia into nitrogen and hydrogen, it is an endothermic process. You are going to absorb the heat from the furnace. By doing so, the NOx formation is going to be strong. Okay, so one way of bringing the CO2 emissions compared with the existing system is to bring the ammonia and blend it with coal or supplementing ammonia in few percentage rather than 100% coal. Okay, now as you all know that steam power plant. So you have the boiler. Boiler is nothing but, I can say, the heat exchanger. You are going to provide the water. This comes from the condenser. So you are going to pump it to the boiler. From the boiler, you are going to take the, I can say, high pressure, high temperature, superheated steam, which is taken into the wood producing device called steam turbine. From that, you are producing the heat energy into mechanical energy. From the mechanical energy, you connect the turbine shaft with the, I can say, generator shaft. You can able to convert the mechanical energy into electrical energy. After extracting the steam, I can say it goes to the condenser. Then going to be condensed. Here the vapor is converted into liquid. Here the liquid is converted into vapor. So here the pressure is increased from low pressure to high pressure. Here the pressure is remains constant. So here the low pressure is raised to high pressure by using a pump. Similarly here the high pressure here is going to be bring down to the low pressure. Okay. So this is steam power. This has as you all know that it has 4 processes. So constant pressure, heat addition, constant pressure, heat rejection, isentropic expansion, then isentropic compression. Here we are going to supply the fuel. For earlier case, mass flow rate of the coal multiply by calorific value of the coal in megajoules per kg. Here, coal I can say maybe few times per hour or kg per hour or kg per second. We get some value here. We are going to supply it to the boiler to produce the heat. Multiply by energy content. Approximately is about 30 to 32 megajoules per kg for coal. You will get some amount of maybe megawatt of energy is going to be provided to produce the required amount of steam in the turbine. Right? Now I am saying that the amount of heat supplied in the boiler is nothing but the mass of the fuel multiplied by calorific value of the fuel. Here is going to be divided into mass of coal times the calorific value of the coal plus mass of ammonia times the calorific value of the ammonia. But I need to say that, or I can say blood, I can say. So heat supplied from the this is supposed to be equal to this is equals to this blood. Accordingly, the ammonia quantity can be added, but ultimately this is fixed. The temperature, high temperature steam needed for the turbine is fixed. Pressure also, both the conditions are fixed. So accordingly, this can be varied. Suitable heat can be added to the boiler so that I am going to get, suppose the steam turbine wants the pressure of, I can say, I need to maintain the pressure of 200 bar. The temperature correspond to that pressure is going to be saturation temperature around 300 or something, but I am producing around 500 degrees centigrade. This condition, inlet steam condition is fixed, but I can vary the quantity of coal. Suppose you want to reduce the quantity of coal from 100% to 10%, or then ammonia to 90%, but the energy content you need for producing this temperature is going to be fixed. So mass balance and energy balance needs to be done. It's purely an energy balance. Accordingly, the power can be produced. Okay. This is with respect to, I can say, steam power plant. This also we can say tried with our, I can say, the internal combustion engine, both petrol and diesel. So ammonia addition in internal combustion engine. So as you all know that the petrol engine is going to allow air and fuel, if you say the carburetor in a cylinder, air and fuel, then you are going to send out the gas after the combustion. So you have a spark plug. So assume that the gas you are using fuel here, fuel, petrol. Now we want to use ammonia. You can send the ammonia along with petrol. That is possible. So manifold induction, that is called manifold induction. Or you can say, suppose the fuel is in the form of ammonia. You want, I can say, you want to inject into the intake side. I don't want to send the petrol in the intake manifold. That's called GDI. You need an injector, gasoline diet injector. Along with you have spark plug going to be mounted on the cylinder head. So the intake manifold, you can allow air along with the ammonia as the form of gas state. You can say, you can inject it. Now, during the suction stroke, you are going to allow air and ammonia, then after completed compression, maybe I can say, in order to enhance the energy content, you can use petrol. Maybe I can say ammonia, maybe I can say 10% energy content. Then this is going to be 90%. So accordingly, you can vary. But anyway, petrol also wants, I can say, one spark plug. Ammonia also wants spark plug because the initial temperature of both petrol and ammonia is more than 700 degrees centigrade. because the compression ratio is nothing but the total volume. Stroke volume plus clearance volume by clearance volume is going to be for petrol is about 8 to 12. Right? So this is nothing but the stroke volume. This is nothing but the clearance volume. So this is nothing but total volume. So total volume to the clearance volume nothing but compression ratio. Even then, if you maintain the total compression ratio, as you all know that from the isotropic process, the temperature final to the initial is equals to pressure final by initial over gamma minus 1 by gamma, which is nothing but the reciprocal of the total volume to the clearance volume, total volume to the clearance volume over gamma minus 1. This is nothing but compression ratio power gamma. Even if you put, I can say T2 by T1 is equals to 12 power 1.4 minus 1. Then take T1 is about 300 Kelvin. You may get T2 is approximately lesser than the ignition temperature of the petrol or ignition temperature of. So you cannot use petrol or ammonia without spark plug. Suppose if you want to replace spark plug, you can put some kind of glow plug. That is the technology they are using in automobile engines. Same way, if you want to use ammonia in a diesel engine, so normally in diesel engine we are inducting only air. Only air is inducted.
Gasoline directly.
We are having a fuel injector here. Fuel injector here. So you may keep two fuel injectors, one for assume that the ammonia is available in liquid state. You may put two fuel injectors, one for diesel, maybe another for ammonia. Suppose you are using ammonia in, I can say, a gaseous state, then you can use ammonia mixed with the intake manifolds. Because what is the advantage in going for, I can say, diesel engine is the air, what we are supplying is about, I can say, for petrol is complementary. We are using at least, I can say, air fuel ratio 100:1. Petrol engine, we need 15:1, but we are supplying lesser than that. Whereas the diesel engine, we need 15:1 approximately, but we are providing 100:1. That's the reason diesel engine will get a very good thermal efficiency in comparison with petrol engine. And all the emissions are coming down. Hydrocarbon, unborn hydrocarbon is approximately 0. Then I can say particulate matter is approximately 0. Particle matter, maybe not particle matter, I can say. Smoke emissions is approximately 0. Then I can say CO2, burning happens, no CO. CO is approximately 0. As the nitrogen is present, NOx is going to be there. So that is not there in the petrol engine. Petrol engine will have more unborn hydrocarbon. I can say more carbon monoxide is also there because we are limiting the oxygen quantity entering into the engine. So in order, if you want to use the ammonia in internal combustion engine, you can use it both in petrol and diesel. But what you can do some kind of slight modification in the engine system to suit whether ammonia is going to add it in the form of liquid state or gas state. Similarly, gas turbine, you can go for a gas turbine. Aviation application also, people are thinking about using ammonia. So simple, I can say gas turbine. You have the air compressor. Compressor goes to the combustion chamber. From the combustion chamber, they are going to take it to the turbine. So the compressor shaft and the turbine shafts are coupled together. Initially, the compressor starts with the help of the battery. How the automotive systems are operated same way. So you need to crank the shaft. When the compressor shaft rotates, you are going to suck the air from the surrounding. When the air enters into the compressor, you are going to compress it. That means assume that the pressure here is P1. At the end of the compression, pressure leaving from the compressor is P2. P2 is greater than P1. that depends on what is the compression ratio. Assume that if it is a reciprocating compressor, it depends on the compression ratio. So P2 is greater than P1. When the pressure increases, naturally temperature also increases. Because volume decreases, pressure increases, temperature increases. Now, the high pressure air entering into the combustion chamber, the air is available, you need to add the fuel. So either the provide petrol or what is the fuel they are using in the aircraft application that can be utilized here. So mass of the fuel along with the air comes from the compressor entering into the combustion chamber. Then you are going to provide the ignition source. Then you are going to get the heat. It's available in the fully gas at high pressure and high temperature. So here I am saying that earlier people are thinking about using hydrogen or ammonia. Hydrogen in liquid state or ammonia in liquid state, or hydrogen in gaseous state, ammonia in gaseous state. Here, the process involved here is called isentropic compression. That means entropy at 1 is equal to entropy at 2. That means Q1 by E1 is equals to Q2 by here. Here is a constant pressure. Theoretically, we are assuming constant pressure combustion. That means assume that I am putting the point number 2 here, point number 3 here. Pressure at 2 is equal to pressure at 2. So no change in pressure in the combustion chamber. Then in the gas turbine, you are going to drop down the pressure from P3 to P4, where P4 is about approximately equal to P1 atmospheric pressure. So here, we are dropping down the pressure from P3 to P4 is about ambient pressure. By doing so, as you all know that work is nothing but specific volume times delta P. Drop in pressure, we get power in terms of kilowatt or megawatt. So here you are going to use the conventional replace the conventional fuel with hydrogen, comes from the ammonia, or the direct usage the ammonia in form of gas and liquid. It's also possible. But how much quantity we can use, whether we can use the hydrogen or ammonia as a sole fuel, people are doing a lot of research in that area. So the big disadvantage here is the amount of energy comes out. We assume that 1 megawatt is power we are producing from the gas turbine. Here, 2/3 of the power, that is nothing but 66.66% of power produced from the gas turbine is used for running the compressor. Suppose I can say 0.66 megawatt power from the turbine is taken for running the compressor. Then what is the useful power from the turbine is about 0.33 megawatt. Okay, the systems are already available. We are going for ammonia or hydrogen. Ultimately, we need at the inlet, we need some temperature and pressure. So accordingly, every fuel has a different energy content that needs to be taken care. Become a key player in carbon neutral industries, offering a solution to cut emissions in energy, transportation, and manufacturing. Beyond its traditional role in fertilizers, it is now seen as a clean fuel, hydrogen carrier, and energy storage medium. Green and blue ammonia production methods enable significant emission reductions, making it a cornerstone of the carbon neutral transition. So this is a global ammonia demand from 2020 to 2050. You can see here, it's a conventional way of producing ammonia shown in the blue color. But the purple color shows the low carbon ammonia, low carbon way of producing ammonia. It is going to be, the demand is going to be remain same. So here is 200, I can say, million metric ton. And then the 2050, the demand needs to be around 650 million metric ton. But what is the contribution from the Haber-Bosch conventional method? Then the low carbon ammonia method is
about I can say in 2030, about 90% they are producing from conventional, 10% from the low carbon source. 2040 is about I can say the 400 million metric tons we are in a demand, the demand is there. Approximately 50-50 from the conventional way of producing the ammonia. The remaining 50% they are coming from green way. 2050, the demand is around 600 million metric ton. About one third of the requirement is from the hammer bush conventional method. Two-thirds comes from the green ammonia source. So the global ammonia market is set to be tripled by 2050. The low carbon ammonia is expected to reach 420 million tons, making up two-thirds of the market according to the global commodity insights. Decarbonization policies are driving its shift from fertilizer production to energy applications like marine fuel and hydrogen carriers. This transformation is forecast to boost global ammonia trade tenfold, with major exports from the Americas and Australia and high demand in Europe and East Asia. So this slide I already presented here. Energy release for with respect to the different the fuels. The gray color represents the energy, the fuel produced from the hydrocarbon source. The green color shows the energy comes out from the green renewable energy. Okay. So diesel, petrol, LPG, ethanol, LNG, methanol. So the diesel, petrol having the higher energy density than the other type of the fuels like LPG, ethanol, and LNG and methanol. In case of the renewable energy source, we can see that among the different green energy source or green fuel, ammonia is going to be having the higher energy density than the hydrogen at the form of liquid or the form of gas state, and it is going to be better than the battery, lithium ion battery. So we want to use the green fuel. Then from this slide, you can come to the conclusion that ammonia is going to be superior than the other kind of fuels. The global ammonia production, you can see here, this is the survey given in 2022. Out of 100%, China is producing 28% of global ammonia. Then Russia 11%, USA 9%, India 8%, Indonesia 4%. The remaining European and other countries are producing 40%. Then 2018, the ammonia production, global ammonia production is 230 million metric tons per annum. When it comes to 2030, is expected around 290 million metric tons per annum. So green ammonia chain, so divided into different categories: renewable production, renewable energy production, plasma water interface, energy carrier, sustainability, tax and fossil fuel. Ultimately, the ammonia comes out, green ammonia. If it comes through the green route by replacing the hydrocarbon, then you can say it's a green ammonia. So here, this the diagram talks about how the green ammonia can be used in different sectors: aircraft, then the marine application, rail application, and as well as the road. So here the processes are there. In order to produce the green ammonia, you need to depend on green renewable energy. I can say the renewable energy is wind, solar, as well as the I can say hydroelectric. Then the process involved for producing the green ammonia is from the electrochemical process. Then is going to be converted into ammonia. The ammonia can be transported either in the form of gaseous state or in the form of liquid state for the different applications. Transportation through ship, or I can say then through the pipeline also is possible. It's going to be used for different applications. Carbon neutrality. What is carbon neutrality? The definition is carbon neutrality refers to achieving net zero carbon dioxide emissions by balancing emissions with removal of or reducing the emission altogether. Okay, so you can see here carbon neutral or net zero. Carbon neutral means you can how much you are producing, how much is going to be absorbed. So both 50%, 50-50.
So I am producing 50 million metric tons of CO2. Same, I can say 55 million is going to be absorbed by the various sources, plantation or I can say the agricultural fields. No, we can find out the method in which how much you are producing is going to be absorbed. So carbon is neutral. But ultimately, I can say I am also thinking about bringing the carbon to zero, remove some equal amount of greenhouse gas as the company creates. India carbon neutrality goals, I can say, China is the leading carbon dioxide emission producer. Per capita income, I can say they are producing 11,535 megatons. US second, third one European, fourth one. So India is the fourth largest CO2 emission, CO2 pollutant emission countries, followed by Russia. India has set a goal of reducing carbon emission by 50% by 2030 and for entire economy to net zero by 2070. The Energy Conservation Act 2022 empowers the central government to specify a carbon credit trading scheme. So, carbon neutral industries. So, how to go for carbon neutral? We need to consume minimum, I can say, energy in the form of hydrocarbon fuel. So, what are the ways? You can see here, you produce the electricity from the renewable source. You incorporate the existing system, carbon capturing system, to absorb the CO2 before it is sent into the atmosphere. That CO2, what is going to be absorbed, or carbon is going to be absorbed from the carbon capturing unit, going to be converted into e-fuel. Maybe I can say, so synthetic fuel. That we can use it in, I can say, different applications, transportation, different transportation, etc. Then the electricity, if you are supplying to the electrolysis process where water can be converted into hydrogen, that hydrogen you can use it in the different transportation sector, or you can use the hydrogen in the fuel cell for producing the electricity, which can be used for running different transportation sectors. Okay. So the ultimate here is what we are going to say is you are not going to discard the actually available conversion system. You can able to reduce the CO2 level comes out either by to the surrounding by capturing the CO2 by carbon capturing systems. Then the carbon captured or carbon dioxide captured from the conversion system going to be converted into synthetic fuel that can also waste to, I can say, fuel you can be able to generate it. That can use it for the whatever maybe the fuel system we are using for conventional fuel we are using for running the different transport sector, you can use it. Other way, so I don't want carbon or carbon based fuel. So then you can go for producing the hydrogen from the electrolysis by consuming the energy from the different renewable sectors. Then that same automobiles, the two-wheeler or four-wheeler or heavy vehicles, right? Shipping, aircraft, you can use hydrogen as a fuel. But rather than the combustion, you are going for electrochemical route, the form of fuel cell to produce the electricity, which can be used for powering the system. Okay. So here we are talking about battery electric vehicle, fuel cell electric vehicle, internal combustion engine, then hybrid electric vehicle. Hybrid means two kinds. You can combine this and this also. It's called hybrid. Plug-in hybrid vehicles also. You can produce the electricity. You can plug in. So ammonia can be burned in engines or used in fuel cell to generate electricity. When used as a fuel, ammonia's byproducts are water and nitrogen. Ammonia can be used to store and transport renewable energy or hydrogen. Ammonia is a more energy dense carrier than hydrogen, and it can be stored at lower temperature. So ammonia, in general, we are used for used as a fertilizer to increase the yield. Ammonia is the key ingredient in nitrogen fixation. We are adding the form of, I can say, sulfates or nitrates, which is essential for feeding the body. The role of ammonia in fuel cell vehicles. So you have in the previous slide we talked about the hybrid system. So we have can see here the hybrid systems are available. So you have the fuel tank, internal combustion engine. Then it's going to be
power is going to be generated in the alternator. The alternator produces power. That power is going to produce, I can say, is to decompose the ammonia which already there in the reactor. Then hydrogen is going to be created. That is going to run the fuel cell. Okay. So the onboard ammonia, onboard hydrogen generation from the conventional fuel also it is possible. So it is very difficult to bring to zero immediately. So we can able to find out the method in which the conventional system can able to bring down the emissions to some level, some percentage. So here the field used for producing the mechanical power. That power is connected to the alternator produce electricity. That electricity used for decomposing the ammonia which is there in the automobile system. So onboard hydrogen is going to be generated. So in order to again say decompose the ammonia, we are supplying two energy sources. One is power in the form of electricity, high grade energy. Another one, the internal combustion engine. After burning the after the combustion happens, you are going to put in the flue gas, which is having the temperature around 600 to 700 degrees centigrade. That heat can be again taken to the reformer for I can say to supplement some percentage. Suppose you want 100% heat, maybe 20 to 30% from the current source, 70% from the waste heat recovery system. Going to use for decomposing the ammonia, then you are going to produce the hydrogen. Hydrogen can be used for running the fuel. So in order to run the fuel cell, you need oxygen. So oxygen we are going to separate out by using a I can say membrane system. So oxygen alone oxygen separated from the air sent to the fuel cell. So the fuel cell you are producing the electricity, heat as well as the water. So you can see here you are producing water, heat and electricity. So in electricity you can use it in the automobile. In the automobile system you need a power. You can charge it in the battery. You can use it for charging the battery for the next step. So here ME means mechanical energy, DR means decombustion reactor, ICE means internal combustion engine, LESB means liquid applied sound barrier. Here, then EPG electronic programming gate. So the total system is electronically operated, so it can able to vary because here the temperature plays a major role. When the temperature comes out from the internal combustion engine for the higher loads is going to be higher, then the minimum energy, high grade energy, going to be consumed from the from the battery or going to come out from the alternator. The remaining energy will be stored in the battery for the remaining operations. The role of ammonia in fertilizer in 2020-2021, around 180 million tons of ammonia were manufactured globally. 70% of which went into creating nitrogen fertilizer, with the remaining share used as an industrial chemical and pharmaceutical. So already we are producing ammonia, but people will not give ammonia just like that to run the engine or to run a steam power plant. So this is more important. Food is more important than the energy. So people, if the excess amount is there, you can able to use it. So instead of depending on the people that are using, I can say ammonia for fertilizer, you can produce the ammonia for the particular application separately rather than depending on the ammonia for used for increasing the crop yield, right? So you can able to have think about the I can say ammonia generation, which can be used for different sectors, not to consume the ammonia what is already produced from the paper process from the different countries. The green ammonia, by using a renewable energy to power the air process, we can significantly reduce the carbon footprint of fertilizer production. This transition can help ensure global food security while minimizing the environmental impact. Ultimately, still they are telling that the green ammonia, they are saying that only for fertilizer. Okay. So if you want to bring down the carbon emission footprint, for producing the ammonia or producing the fertilizer, and also you are producing carbon emissions for running the internal combustion engines on road or off the roads or the industries, that ammonia can be produced separately. That's not going to be, I can say, there's always food versus the energy, right? So you cannot take the the ammonia for already they are in need of for producing the I can say fertilizer. So nitrogen fertilizers are you come across many fertilizers, but the major thing is the nitrogen fertilizers, ammonia is going to be there. So now the role of ammonia in energy carrier. So we are going to eliminate the conventional process going for I can say green method. So hydrolysis, air separation unit, Haber-Bosch. Then Haber-Bosch is the process of producing ammonia. Then you need a cracking system to convert the I can say ammonia into hydrogen and nitrogen, and then it's the energy balance, right? So here they are talking about the production of ammonia, right? Per ton of ammonia production, right? We are consuming about 33 to 38 gigajoule, 10 power 9 joule per ton. Here, the consumer side, in order to convert the ammonia into the hydrogen for different application, we are consuming about 8.4 gigajoule to 10.7 gigajoule. Total, suppose you want to convert, I can say water into hydrogen, right? Which can be used as a fuel in the fuel station. 38 plus 10.7 and about I can say 40, you can assume the 11, about 49 gigajoules per ton. Gigajoules of energy you need to produce one I can say ton of ammonia or 1 ton of I can say hydrogen. The role of ammonia. So we are majorly I can say the ammonia. The fuel we want to use as a fuel. The major target is they are targeting on ship marine industry. So it consumes the maximum I can say the liquid fuel or the coal, or it's going to produce the maximum CO2 in the marine sector. So their focus majorly on for the I can say the marine field. They are planning to use ammonia as a fuel for moving the ship. So this ammonia is also used as a fuel in the engine, and already we discussed that. You can use it as a sole fuel, or you can use it as a blend. Challenges: use ammonia as a marine fuel, toxicity and safety. You need to take care of it. Ammonia toxic requires stringent measures in handling, storage, and transport. Effective containment and monitoring system are crucial. Engine technology and infrastructure, because it is highly corrosive in nature. All the components associated with the fuel dealing with is going to be put utmost care in fabricating the particular component, corrosion-free environment. Then oxides of nitrogen is going to be another issue. Apart from the oxygen, the nitrogen is supplying from the air. We are also supplying nitrogen from the fuel. So ammonia generation is going to be higher compared with the diesel. If you are using diesel alone, so the ammonia generation, I can say the NOx emission is going to be very high. In case of ammonia, if you use the fuel, we need to bring some kind of technology. It's a technology. They can able to add the system in the exhaust side, bring down the NOx to the as per the emission norms. Already in Japan, people are now using ammonia as a fuel in thermal power plant. 20 to 30% they are using. Their aim is to replace the coal to 100% ammonia. So they are currently going for 30% ammonia and 70% coal. They eliminate the carbon dioxide emissions to some level. But in 2030 or up to 2040, they are going to completely eliminate the coal to go for only ammonia as a fuel for all them. Similarly, ammonia is going to play a major role in our steel industry. We need energy. So a lot of coal or a lot of the liquid fuels or gases fuels are used for having carbon and hydrogen going to be used as heat source for melting this iron ore. So here the ammonia is going to be if you are going to I can say use ammonia as a fuel in steel industry, then we can able to bring down the greenhouse emissions. Well, the cement industry also, we can able to, lot of energy intensive industries, they are able to use ammonia as a fuel, we can able to bring down the emissions. So getting to net zero carbon emissions by 2050, go for a renewable resource, increase the solar and wind capacity 3.5 times, about 500 gigawatt. Eliminate the most electricity generation from coal. Maintain current natural gas generating capacity for reliability. Because why they are saying natural gas is the carbon content in the natural gas, the form of methane, comparatively lower than if you are dealing with, let's say, high density liquid or the coal, which has a carbon value more than I can say 5. So when you are able to use hydrocarbon fuel, it's a lower carbon side, the carbon dioxide which comes out from the products of combustion is going to be lower. That's the reason why I'm saying that. Enforce usage of the natural gas for eliminating liquid or the solid fuel coal. We can able to reduce the CO2 to some level. Then increase zero emissions, vehicle sales share up to 50%. Increase sales share of building heat pumps. So instead of using an electrical heater to heat the room, particularly in the places like Srinagar and Delhi or the northern places where during the winter the temperature goes very near to 5 to 10 degrees centigrade. So instead of going for using an electrical heater, high energy source for maintaining the room temperature of 25 to 26 degrees, you can go for heat pump. Providing the energy in the form of heat, we can able to reduce the energy consumed for maintaining the room temperature. So provide the low grid energy rather than high grid energy, you can able to reduce the CO2 emissions. All new buildings and like appliances are maybe equipped with green energy concept. You can able to bring down the I can say CO2 level. You can meet the demand what suggested in 2030. Research and development for carbon capture, and it's a CO2 absorption and carbon neutral fuels needs to be explored. So I can say it's not going to be bring down immediately to zero, but you can capture that CO2 which is present in the free gas, but you convert it to some kind of product. Then that way also you can able to bring down the CO2 emissions. Build the electricity transmission and pipelines for CO, carbon dioxide and hydrogen gas. Okay. So these are the references and we have used for preparing the PPT. So the outcome of the presentation is we cannot bring down the CO2 emissions to zero immediately, but there are ways to bring down to zero. It takes its own time because we already damaged the environment. We cannot bring the CO2 to zero. We can bring very near to CO2 neutrality first by bringing the carbon-free fuel, which is going to be used as a supplementary fuel in the conventional system called aircraft applications, then the steam power plant and the gas turbine systems, and the industries where the energy intensive industries like steel industry, cement industry, leather industry, pharmaceutical industry, bringing some kind of cogeneration system where we can able to use the ammonia as a fuel to bring down the CO2 emissions. By doing so, maybe in not in 2030, maybe 2040 or 2050, we can bring carbon neutral. How much we produce is going to be balanced. Thank you so much for your attention. And if you have any questions, please. Okay, if there's no question, then we can wind the end of the session now. Break for tea. We'll be back by 11:30 to Thermal.